My name's Dr Matt Telfer and I'm a lecturer in physical geography at the University of Plymouth. I've been studying dunes for about 15 years now, initially at the Universities of Sheffield and Oxford, and then since 2010 at the University of Plymouth. And originally I was coming from the perspective of finding out what dunes on Earth can tell us about Earth's history. But the more I looked into that, the more I realised that there's still really fundamental things we don't understand about how dunes form in the first place. My interest in the dunes on Pluto came about as a result of a conference in 2014, where I presented some analysis I'd been doing on terrestrial dunes using remotely sensed data to analyse the patterns. And all of the interest I got from that really was in people working on planetary dunes rather than Earth dunes. Prior to New Horizons mission, the best imagery we had of Pluto was just 12 pixels across the entire planet. So we knew very, very little about what we'd expect in any respect. Yes, as you rightly point out though, there's so little atmosphere. There's something like 1/100,000th the atmosphere of Earth. So how we could have wind to move particles around to make dunes was a different question. To create dunes, you need three things. You need a granular surface of some kind. Now on Earth, that's typically sand, but it could be snow. We have dunes in Antarctica as well. You need a non-cohesive surface, so one that isn't tied together too much with perhaps vegetation or simply with moisture. And lastly, you need sufficient wind. So you need wind of enough power to be able to pick up and mobilise those grains and throw them into the air where they can subsequently deposit and form a dune. Initially looked at these features, which seemed so similar to Earth's dunes, we were at a little bit of a loss to explain how that could be the case, because there is so little atmosphere to create the wind. Getting a granular material isn't so difficult, because we know that there are possibly nitrogen, methane, and carbon monoxide frosts and ices on these planets, and they can form granular material. Getting a non-cohesive surface wasn't too difficult either, because there's no moisture and obviously we don't have vegetation to worry about on Pluto. The tricky bit was trying to work out how we could get enough wind to move the grains. And this came about really from a very fortuitous collaboration with one of my German colleagues who'd been doing the numerical modelling and suggested that if you could get the grains airborne in the first place, then they would keep going. That then left us needing a mechanism by which we could get the grains airborne in the first place. And it turns out from additional modelling that we've done, that where we've got a mixture of nitrogen and methane ices on the surface, the nitrogen will sublimate more readily and effectively will fling the methane grains into the air. And once that process is started, we get a sort of runaway effect, because as each grain lands, it splashes, it knocks more grains into the air. What these findings tell us is that Pluto has a really dynamic surface geology. We know these features are relatively geologically young. These are not fossil features that have been there for millions of years. And so they show us that despite this far-flung world being so remote from our own planet, there's still a lot that we can recognise with our own Earth system, and a really diverse, young, active geomorphology and geology. And it really focuses in on the surface-atmosphere interaction. And Pluto's atmosphere is very unusual. It's the only body in the solar system where we believe the atmosphere is currently escaping. So learning more about how this process is going on is informing us of the real fundamentals of planetary formation. We do plan to take this research forward in the future. Now, obviously we're a little bit limited here because that spacecraft flew for 9 years and was a good 10 years or more in the planning prior to that. There are no immediate plans for another flyby of Pluto, so we're in one respect hamstrung by the fact that we're not going to see any more new data. That's it. That's what we've got for the next probably 20-30 years at minimum. So there's a couple of directions we're using to take that forward. This process by which the grains are ejected in the first place is something that we want to develop further. We want to model that further. There's still analysis of the imagery to do. We can use image processing techniques to estimate a height for the dunes, for instance, which we don't currently have. And lastly, on the 1st of January of next year, so January 1st, 2019, the New Horizons craft is going to fly past another of these so-called Kuiper belt objects, these small outer planetary bodies. And there, once again, we know very, very little about what we'll find. This body is a good deal smaller than Pluto. It's going to fly even closer to it than last time. So really, we'll be eyes peeled on the imagery as that comes back shortly after January the 1st at the beginning of next year.